Hello, my name is Thomas. I'm here with my colleague Jesslyn. We're to present you our project, which is a photogrammetry based 3D scanner. Now this project was brought to us by the McGill Additive Manufacturing Student Society, otherwise known as MAMS. So they approached us because they needed a way to help them with their 3D scanning activities, or photogrammetry activities. Now, what is photogrammetry? Well, it's a 3D scanning process which includes just two main processes. It's first you have to take photos of a physical object from all angles, and then take these photos and put them in a special software to stitch them and create a point cloud or a virtual replica of that object. Now, our project focused mainly on the photo taking part. So we recreated a system that automatically takes all these photos from different heights, angles, and distance from the object.
Essentially, MAMS is working with both the anatomy department here at McGill as well as the Red Pat Museum. And they both had different collections that we had to scan, one being a wax model and the other being various artifacts. Now, these models set a limitation on our system, being its volume of the objects that we had, as well as the weights of the objects. Now, we also wanted to make sure that this process was quick and as well as produce high quality images. Now, this process took a total of 8 months, the first half being us designing the systems, including a 3D CAD, various PCB designs, and code architectures. Finally, we put this all together and we made our final working system, which we'll explain to you later, which consisted of mechanical, electrical, software systems. Our mechanical system is broken up into 4 main components. There's a rotational base, a wrist that incorporates the camera, an X and a Y motion. Now, for the base, we're using a brushed DC motor with a encoder that's placed in the very center so that we can read the angle of the actual base and the model that's placed on top of it. We get up to 1 degree of accuracy with this system. This is then coupled to a RY system, which allows us to move this rig, which the camera is located on top of, up and down. Now, this motor is slightly different. With a rotary encoder placed into the motor, we're able to track the position of our carriage as it moves up and down and have up to a centimeter of accuracy. This driving motion is done by our pulley system that we have here, with a dynamic tensioner at the bottom to accommodate for tensions on either side of the belt, depending on the motions going upwards or downwards. This system is then coupled with a wrapping pinion for our X motion. With a motor that's driving a gear in the center over here, this drives our system outwards and inwards with a limit switch so that we can reset our position to our new 0. This system finally has a servo motor, which will be moving the angle of the camera so that we can take pictures of the object while we're very on top of it or even underneath it. For our electrical system, we started off by looking at power. What we're using is a 12-volt DC power supply that is used to run our whole systems and plugs into a normal wall outlet. This system then provides power to our 2 systems. The first, which takes care of our X control as well as our wrist control, and the final one, which allows us to lift the Y system as well as rotate the base. Now, each of these PCBs take into consideration 4 main aspects. There's a brushed motor that needs to be driven, a servo motor, limit switches, as well as rotary encoders that need to be read. Maximum that we have per system is up to 2 motors, 2 rotary encoders, 1 servo, and 1 limit switch. So because of these limitations and the similarity that we have across our system, we designed a PCB that was similar on both aspects so that we can have a more modular system.
In order to automate our process, we use a master-slave configuration where a laptop acts as the master node and is connected to all the slave subsystems through a USB hub. Now, the 2 subsystems are 2 custom PCBs here and the camera, which is usually attached right here. On the master node lives a C++ application which integrates the Canon SDK in order to be able to send commands to our Canon DSLR camera. Those commands are changing the aperture of the camera, the shutter speed, the ISO of the camera, and of course a command to take a picture whenever we wanted to through our program, of course. Now that same C++ application also implement a custom, our custom synchronous communication protocol, which is used to send commands to to the Arduinos, which are on our custom PCBs. Briefly, how it works is through this protocol, we're able to send commands to either move the motor or get some status on any of the motors in the system, and that logic is handled by the embedded software that lives on the Arduinos.